Our entire observable universe is just a tiny bubble in an unimaginable vastness. We are about to journey to the very edge of that bubble, where the known laws of physics strain and break. You will explore 30 of the most profound cosmic mysteries, from the true nature of dark energy to the shocking possibility of a multiverse. We will confront the gravitational enigma pulling thousands of galaxies and ask if our universe is truly alone. By the end, you will see the cosmos not as a static picture, but as a living, expanding frontier of unanswered questions. Which single mystery about the edge of everything do you find the most compelling? This bubble of everything we can ever see has a hard edge, a final frontier defined not by distance, but by time itself. We call this the observable universe, and its boundary is simply the limit of how far light has been able to travel in the 13.8 billion years since the cosmos began. The oldest light that reaches our telescopes is the cosmic microwave background, a faint afterglow from when the universe was a mere infant, just 380,000 years old. This is our ultimate horizon, a baby picture of the cosmos printed across the entire sky. Yet this horizon is not a physical wall. It is a wall of information, a barrier created by the finite speed of light. The profound implication is that there is almost certainly more universe, much more, lying beyond what we can observe. What could that unseeable realm be like? Does it continue with more galaxies, stars, and planets in an endless cosmic tapestry? Or does the very nature of reality change beyond that informational veil? This first mystery forces us to confront a humbling truth. Our entire cosmic map, every galaxy we have ever catalogued, is just a single island in an ocean whose true size remains one of the greatest enigmas of all. But that cosmic horizon is not the only invisible force shaping our journey. Our own Milky Way galaxy is not drifting aimlessly through the void. It is being pulled, along with thousands of other galaxies, toward a specific point in space, a gravitational ghost known as the Great Attractor. Imagine every star, every planet, every speck of dust in our galactic neighborhood caught in a slow, relentless river, all flowing toward a mysterious destination we cannot even see. The source of this immense pull lies in the direction of the constellation Centaurus, but it is hidden from our direct view by the thick, dusty plain of our own galaxy. Astronomers call this region the zone of avoidance, a name that perfectly captures its frustrating nature. It is like trying to see a distant city while standing in a dense, permanent fog. For decades, this cosmic fog bank kept the Great Attractor's true identity a profound secret. What could possibly possess enough gravitational muscle to tug on so many galaxies, including our own? Early theories suggested it was simply a massive concentration of matter, perhaps a supercluster of galaxies of unimaginable scale. But as our observational tools improved, allowing us to peer through the galactic dust with X-ray and infrared eyes, a more complex picture emerged. The Great Attractor is indeed a huge concentration of mass, but it now appears to be just one part of an even larger structure, a gravitational nexus where multiple superclusters are converging. Some have even speculated about more exotic possibilities, like a cosmic string or a gravitational anomaly from a different dimension, though these remain far less likely. The true lesson of the Great Attractor is not just about one hidden object. It reveals that the universe on its grandest scales is woven together by these immense, invisible filaments of dark matter and galaxies, a cosmic web where entire clusters are drawn toward the densest nodes. Our local journey toward this unseen attractor is just a small part of a much larger and even more mysterious flow. This immense cosmic flow is not the only large-scale structure defying our expectations. While the Great Attractor represents a dense knot in the cosmic web, other regions present the exact opposite puzzle, vast deserts of near-total emptiness known as cosmic voids. The most famous of these is the Boötes void, a spherical region of space so staggeringly large that it could contain thousands of galaxies like our Milky Way, yet it holds only a few dozen. If you were to place our galaxy at the center of this void, we might not have even discovered other galaxies until the 1960s, our telescopes simply finding nothing in the immense darkness for hundreds of millions of light years in every direction. The existence of such profound emptiness challenges the very foundation of how we believe the universe evolved. According to our best models, matter after the Big Bang should be distributed in a relatively even, frothy pattern, with galaxies forming along the dense filaments of dark matter. The Boötes void is not just a gap in that web, it is a chasm so vast it seems to break the rules. How could the process of galaxy formation simply skip over a volume of space that immense? What force or circumstance prevented gravity from pulling matter together here when it succeeded so spectacularly everywhere else? The leading theory suggests these voids are not completely empty, but are instead filled with dark matter, the invisible cosmic scaffolding that makes up most of the universe's mass. Perhaps in these regions, the dark matter was not dense enough to trigger the formation of many luminous galaxies, leaving behind a ghostly, transparent landscape. Another, more speculative idea is that voids are expanding faster than the universe itself, their internal gravity too weak to resist the relentless push of dark energy, effectively blowing them up from the inside out. These are not just barren spaces, they are active participants in the cosmos's evolution, their growing emptiness subtly shaping the fate of the galactic clusters that surround them. The mystery of the Boötes void forces us to ask a haunting question. Is this immense nothingness a rare flaw in the cosmic tapestry, or is it a sign that our understanding of the universe's structure is fundamentally incomplete, hinting at forces and initial conditions we have yet to imagine? These vast cosmic voids are not just expanding, they are accelerating into nothingness, and this acceleration is the single most shocking discovery in modern cosmology. For most of the 20th century, scientists believed the universe's expansion was slowing down, gradually coasting from the force of the Big Bang against the relentless pull of gravity. Then, in the late 1990s, two teams of astronomers made a measurement that turned everything upside down. They were observing a specific type of exploding star, a supernova that acts as a standard candle, allowing for precise distance measurements across billions of light years. By comparing how bright these supernovae appeared with how much their light had stretched or red-shifted, they could clock the universe's expansion rate throughout its history. The data revealed something impossible. The most distant and therefore oldest supernova were dimmer than expected. This meant they were farther away than anyone had predicted, proving that the expansion of the universe is not slowing. It is speeding up. Some unknown repulsive force working against gravity on the grandest scales is pushing galaxies apart at an ever-increasing rate. This mysterious force was given a name, dark energy. We now know that dark energy is the dominant component of our universe, making up about 68% of everything that exists. Its nature is the paramount mystery at the edge of physics. The leading and simplest explanation is Einstein's cosmological constant, a kind of innate energy woven into the very fabric of empty space itself. Imagine the vacuum of space is not truly empty, but is constantly seething with virtual particles that pop in and out of existence. This quantum activity could generate a constant, gentle pressure that pushes the universe apart. The problem is, when physicists calculate how strong this vacuum energy should be, the theoretical value is off by a factor of 1 followed by 120 zeros. It is the worst prediction in the entire history of science. This colossal failure has led to other, more dynamic theories. Perhaps dark energy is not a constant, but a new kind of energy field that changes over time called quintessence. If this is true, its repulsive strength could either weaken or intensify in the future, leading to wildly different cosmic fates. The ultimate question is, what will this runaway expansion do to our universe in the far future? If dark energy remains constant, it will lead to a slow, cold death, where galaxies are torn beyond the cosmic horizon from one another, leaving isolated islands of stars in an ever-cooling, infinite blackness. But if quintessence grows stronger, it could result in a far more violent end, a big rip where the fabric of spacetime itself is torn apart, shredding galaxies, stars, planets, and even atoms. Dark energy is not just a curiosity, it is the force that holds the final chapter of our cosmos in its invisible hands, and we have only just begun to read the first word. While dark energy pushes the cosmos apart, another, even more elusive component holds it all together. This is the mystery of dark matter, an invisible substance that makes up roughly 27% of the universe. Its presence is felt only through its immense gravitational pull, a ghostly force that sculpts the cosmos on the grandest scales. Without it, our galaxies would simply fly apart. The evidence for this unseen cosmic scaffolding began nearly a century ago with astronomer Fritz Zwicky, who noticed that galaxies within a distant cluster were moving so fast that the gravity from their visible stars was hopelessly inadequate to keep them bound together. He proposed the existence of dunkel materie, or dark matter, to provide the missing mass. Decades later, Vera Rubin provided irrefutable proof by studying the rotation of individual galaxies. She found that stars at the outer edges of spiral galaxies orbit just as fast as those near the center, a motion that defies the laws of gravity unless the galaxy is embedded within a massive, invisible halo of matter that extends far beyond its visible stars. The most striking visual evidence for dark matter came from observations of the Bullet Cluster, a spectacular collision of two galaxy clusters. When astronomers mapped the mass using gravitational lensing, they found that the bulk of the mass, the dark matter, had sailed right through the collision untouched. Meanwhile, the normal gaseous matter was slowed and heated, lagging far behind. This proved dark matter does not interact with itself or with normal matter through any force except gravity. It is truly a shadow universe, intermingling with our own yet completely intangible. So what is it made of? The leading hypothesis points to a new, undiscovered type of fundamental particle, one that is heavy, slow-moving, and incredibly reluctant to interact with the ordinary particles we know. For decades, physicists have been hunting for these particles with increasingly sensitive experiments deep underground, hoping to catch the faintest bump from a dark matter particle colliding with an atomic nucleus. They have also tried to create them in powerful particle colliders like the Large Hadron Collider. So far, every search has come up empty. This persistent silence is deepening the mystery, forcing scientists to consider more exotic possibilities. The discovery of a dark matter particle would be a monumental breakthrough, finally revealing the identity of the universe's primary architect. It would not only explain how galaxies formed and evolved, but would also illuminate the ultimate fate of the cosmos, determining whether the relentless push of dark energy will ultimately triumph, or if the gravitational grasp of dark matter can hold the cosmic web together for an eternity. The shadowy presence of dark matter and the repulsive force of dark energy might be the dominant players in our cosmic story, but they are not the only possible actors on the stage. This leads to one of the most radical ideas in all of science, the concept of a multiverse. What if our entire universe, with its hundreds of billions of galaxies and its specific, finely tuned laws of physics, is just one single bubble in a vast, frothing cosmic ocean of other universes? This is not mere science fiction. The idea emerges naturally from our best attempts to explain the Big Bang and the fundamental forces. The theory of cosmic inflation, which describes the universe's explosive initial growth, suggests a process called eternal inflation. In this scenario, the inflationary energy that drove the Big Bang never completely turns off. Instead, it decays in patches, with each patch becoming its own separate, expanding bubble universe forever disconnected from our own. Our entire cosmos would be just one such bubble in an infinite, ever-growing multiverse. String theory, a leading candidate for a theory of everything, adds another layer. It suggests the properties of our universe, like the strength of gravity or the mass of an electron, are determined by how tiny, vibrating strings of energy are curled up in extra, hidden dimensions. The mathematics of string theory points not to one unique solution, but to a staggering number of possible configurations, perhaps 10 to the power of 500. Each configuration could represent a different universe with different physical laws. This is known as the string theory landscape, a vast cosmic catalog of possible realities. There are other versions of this mind-bending idea. The many worlds interpretation of quantum mechanics proposes that every time a quantum event has multiple possible outcomes, the universe splits, creating a new branch for each possibility. In one branch you turned left, in another you turned right, and both realities are equally real, playing out in a limitless tapestry of parallel timelines. The scientific debate surrounding the multiverse is fierce. Is it a genuine, testable scientific theory, or is it untestable philosophy? Critics argue that if these other universes are permanently disconnected from ours by definition, then we can never observe them or gather any evidence. This, they say, places the multiverse outside the realm of science. Proponents counter that we might find indirect evidence. For instance, if our universe collided with another bubble universe in the distant past, the imprint of that colossal collision could be etched into the cosmic microwave background, a scar on the baby picture of our cosmos. The philosophical implications are equally staggering. If the multiverse is real, then every possible reality exists somewhere. There are universes where life never formed, and universes where it flourishes in forms we cannot imagine. This could provide a dramatic answer to the question of why our universe seems so perfectly fine-tuned for life. If there are an infinite number of universes with different physical constants, then it is no surprise that we find ourselves in one of the rare, lucky ones where those constants allow for stars, planets, and life to exist. We are not the purpose of the cosmos. We are simply a happy accident in a much wider and far stranger reality. The search for these ghostly sibling universes is already underway, not with telescopes pointed at distant stars, but with sophisticated algorithms scanning the oldest light in existence. Scientists are meticulously analyzing the cosmic microwave background, that fossilized echo of the Big Bang, searching for telltale bruises or discolorations that could mark the spot where our infant universe bumped into another cosmic bubble. The logic is compelling. If our universe is just one bubble in a frothing multiverse, and if that inflation is eternal, then other bubbles are inevitably forming and expanding all around us. In the seething energy of the early cosmos, the boundaries of these bubbles could have occasionally touched. A collision between two expanding universes would have sent shockwaves rippling through the very fabric of space-time, creating a distinct circular pattern of hot and cold spots imprinted on the cosmic microwave background. It would be a cosmic scar, a permanent record of a meeting with another reality. Finding such a signature is incredibly difficult. Researchers must sift through the subtle temperature variations of the microwave background, looking for specific statistical anomalies that cannot be explained by the standard model of cosmology. It is like trying to find a single, unique fingerprint on a globe the size of the Earth. Some teams have even claimed to have found potential candidates, curious circular patterns in the data that stand out from the random noise. Yet these findings remain controversial and unconfirmed, requiring more precise data from future space missions and ground-based observatories. The implications of a confirmed detection are almost beyond comprehension. It would be the ultimate Copernican revolution, proving that our entire cosmos is not the entirety of existence, but merely one province in an infinite metaverse. Such a discovery would instantly answer some of our deepest questions while opening up a vast new frontier of even more profound mysteries. We would know for certain that reality is far grander and more bizarre than we ever dreamed, a realization that would fundamentally and permanently alter our understanding of our own place in the totality of everything. Even if we accept the grand possibility of a multiverse, a stubborn puzzle remains right here in our own cosmic backyard. Why does the universe look so remarkably uniform in every direction we look? The ancient light of the cosmic microwave background shows a nearly identical temperature everywhere, a perfect thermal equilibrium. This presents a profound logical problem known as the horizon problem. For two regions of space to reach the same temperature, they must have been in thermal contact, able to exchange energy and balance each other out, like two cups of coffee that eventually cool to the same room temperature. The problem is, the most distant points we see on opposite sides of the sky were never close enough to interact. In the standard Big Bang model, there simply has not been enough time since the beginning for light or any influence to have traveled between them. Those regions are, and always have been, beyond each other's cosmic horizons. So how did they coordinate their properties so perfectly? It is as if you met a perfect stranger on the other side of the world who not only spoke your language but also had your exact same thoughts and memories without any prior contact. To solve this paradox, physicists proposed a dramatic revision to the universe's earliest moments, a theory called cosmic inflation. This idea suggests that in the first tiny fraction of a second, a minuscule speck of the primordial universe underwent a phase of hyper-fast exponential expansion. For a fleeting moment, the universe blew up in size by a factor of at least 10 to the 78, far faster than the speed of light. This unimaginable growth stretched a single, tiny, causally connected region into a volume much larger than our entire observable universe today. Every part of our cosmic horizon was once crammed into that same infinitesimal point, allowing it to smooth out its temperature and density before being inflated to cosmic proportions. This is why the universe looks so uniform. The entire sky was once a single, cozy neighborhood before being stretched into the vast cosmos we see. But inflation did more than just solve the horizon problem. It also provides the origin story for all the structure in the universe. According to the theory, the vacuum of space during this inflationary period was not perfectly calm. It was subject to tiny, random quantum fluctuations, minute ripples in the fabric of reality. As the universe inflated at a staggering rate, these microscopic ripples were stretched to astronomical sizes. The slightly denser regions in this quantum foam became the gravitational seeds around which dark matter and eventually galaxies would later clump, drawn together by their own extra gravity. The entire cosmic web of galaxies, clusters, and voids we observe today is therefore a magnified imprint of these quantum jitters from the first moment of time. The grand tapestry of the cosmos began as subatomic whispers. The challenge, however, is that inflation is a powerful and elegant theory, but we still lack the smoking gun, the direct, unambiguous evidence that it truly happened. The most promising clue would be the detection of primordial gravitational waves, ripples in space-time itself generated by the violent inflationary expansion. These waves would have left a distinct curling pattern in the polarization of the cosmic microwave background, a specific signature often called B modes. Finding this pattern would be like discovering the fossilized footprints of the Big Bang's explosive birth. Several ambitious experiments are scanning the sky for this faint signal, but so far it remains elusive. The quest to confirm cosmic inflation is a drive to witness the very first instance of creation, to understand not just how our universe evolved, but how it was born from almost nothing at all. This smooth, uniform cosmos predicted by inflation now faces a startling anomaly. Hidden within the seemingly random temperature map of the cosmic microwave background is a strange and controversial pattern that some scientists have dramatically nicknamed the axis of evil. It is not a single feature, but a mysterious alignment of several large-scale structures in this ancient light. The hot and cold spots, the echoes of the universe's infancy, appear to be correlated in a way that suggests a preferred direction in space, a kind of cosmic axis. This discovery strikes at the very heart of a foundational rule of cosmology, the cosmological principle. This principle states that the universe on large scales is isotropic and homogeneous. In simple terms, it should look the same in every direction and have no special place or preferred axis. There should be no up or down, no left or right on the cosmic scale. The axis of evil, if real, would be like finding that all the continents on Earth were subtly tilted to point toward one specific star in the sky. It suggests the universe might have a grand architecture, a fundamental lopsidedness that we are only just beginning to perceive. So what could this strange alignment be? The most conservative explanation is that it is simply a statistical fluke. When you look at any large set of complex data, you can sometimes find patterns that appear significant purely by random chance. It is like finding a cloud that looks exactly like a face, a coincidence of nature that means nothing. Another possibility is that it is not a feature of the universe at all, but an artifact of our measurements. Perhaps our own solar system's motion through the cosmos, or even leftover radiation from within our own Milky Way galaxy, is creating a contaminating signal that imitates this axis. Scientists have worked tirelessly to subtract these local effects, and the alignment stubbornly persists. This leads to the most thrilling possibility that the axis of evil is a genuine clue to new physics. Could it be a remnant from before the Big Bang, a fingerprint of some exotic structure in the multiverse that tugged on our infant cosmos? Or does it hint that the fabric of spacetime itself has a subtle, underlying grain, like wood, that breaks perfect symmetry on the largest imaginable scales? For now, the axis of evil remains an unsolved and deeply puzzling mystery. It is a celestial whisper that our most cherished assumptions about the universe might be incomplete, a ghost in the machine of creation that refuses to be ignored. This cosmic alignment, this potential axis, is a question about the universe's structure, but an even grander question looms over all of them. Where is this entire cosmic journey ultimately headed? The fate of everything from the largest galaxy to the smallest atom hinges on the unknown nature of dark energy, and scientists have outlined three possible endings for our cosmos. The first, and currently the most likely based on our observations, is the Big Freeze, also known as heat death. In this scenario, dark energy remains a constant force, and the universe continues expanding forever at an accelerating rate. Galaxies will be pulled farther and farther apart, their light eventually red shifting into oblivion. Within each galaxy, stars will slowly burn through their fuel one by one until the last star flickers out. The universe will become a vast, ever-cooling graveyard of black holes, dead stars, and frozen planets, drifting in an eternal and ever-deepening darkness. All activity, all heat, all life will eventually cease as the cosmos reaches a state of maximum entropy, a final, uniform coldness. It is a slow, quiet, and profoundly lonely end. A second, far more violent possibility is the Big Rip. This scenario depends on dark energy not being constant, but instead growing stronger over time. Imagine this repulsive force intensifying until its push overwhelms every force that holds things together. First, the accelerating expansion would tear apart galaxy clusters, then individual galaxies. As the force grows, it would rip stars from their galaxies. In the final, terrifying moments, the fabric of spacetime itself would be shredded. The gravitational bonds holding planets together would snap, followed by the electromagnetic forces holding your very body together. In an instant, every molecule, every atom, and every fundamental particle would be torn asunder, ripped apart by the ever-increasing vacuum of space. The universe would end not with a whimper, but with a catastrophic, instantaneous disintegration of reality itself. The third classic ending is the Big Crunch, a dramatic reversal of our current expansion. This would require dark energy to weaken and eventually reverse its effect, allowing gravity to finally win the cosmic tug of war. The expansion of the universe would slow, halt, and then begin to run in reverse. Galaxies would start rushing back toward each other, the sky heating up as the cosmic background radiation is blue shifted into a searing glare. The universe would collapse back in on itself, all matter and energy pouring back into a single ultra-hot, ultra-dense point, a mirror image of the Big Bang. Some theories even suggest this could trigger a new Big Bang, leading to an endless cycle of cosmic death and rebirth, a perpetual series of universes with no beginning and no end. So which destiny is ours? Current measurements of the accelerating expansion strongly point toward the Big Freeze. The cosmological constant, a steady dark energy, fits our data best. The violent Big Rip and the cyclical Big Crunch are, for now, less favored by the evidence, yet our understanding of dark energy is still in its infancy. A tiny shift in its properties over billions of years could completely alter the final chapter. The ultimate fate of the cosmos is not yet written, and the pen is held by the greatest mystery of them all. The ultimate fate of the cosmos hinges on dark energy, but its final chapter depends on something even more fundamental, the very shape of space itself. This is not a shape we can easily picture, like a ball or a saddle. It is the geometry of the universe on its grandest possible scale, the curvature, or lack thereof, of the entire cosmic stage. Scientists have narrowed the possibilities down to three. The universe could be closed like the surface of a sphere where parallel lines would eventually meet. It could be open, curved like a saddle where parallel lines would diverge. Or, and this is what all our best measurements indicate, it could be perfectly flat. To understand this, imagine trying to draw a giant triangle across the cosmos with beams of light as its sides. In a closed, spherical universe, the angles of that triangle would add up to more than 180 degrees. In an open, saddle-shaped one, they would add up to less. In a flat universe, the rules of geometry we learned in school hold true, and the angles add up to exactly 180 degrees. The most powerful tool for drawing this cosmic triangle is the cosmic microwave background. The tiny temperature fluctuations in this ancient light act as imprints of a specific size, a standard ruler frozen in time when the universe was only 380,000 years old. By meticulously measuring the apparent size of these ripples on our sky, astronomers can deduce the geometry of the space between them. The result, confirmed with stunning precision by missions like Planck, is that the universe is flat too, within a margin of error of just 0.2%. The implications of this flatness are staggering. A flat universe is likely infinite, stretching on forever without end. More profoundly, the geometry of the universe is dictated by its total density, the combined amount of all matter and energy, both dark and normal, within it. A flat universe means the density is at a precise, critical value, perfectly balanced between the forces of expansion and gravitational collapse. It is like a cosmic tightrope where the slightest deviation in density at the beginning would have caused the universe to either rapidly recollapse or expand so fast that no galaxies could ever form. The fact that we observe this perfect flatness, this exquisite balance, is one of the most profound fine-tuning problems in all of cosmology, forcing us to ask why the cosmos is poised on this razor's edge. This perfect cosmic flatness, this delicate balance of all existence, forces us to ask a much more basic question. What is the universe actually made of? We have dark energy and dark matter, but what about the ordinary stuff, the atoms that build you, me, and every star we can see? Astonishingly, we cannot even find all of that. Cosmologists have a precise inventory for the universe's contents, derived from the Big Bang's own chemistry. When they count up all the normal matter, the protons and neutrons known collectively as baryonic matter, in all the stars, galaxies, and cold gas clouds we can see, more than half of it is simply missing. It is a cosmic accounting error of epic proportions. The ledger shows the money was spent, but we cannot find where it went. This is the mystery of the missing baryons. The predicted amount of ordinary matter is firmly established by our measurements of the cosmic microwave background, which acts as a fossil record of the universe's initial elemental brew. Yet when we add up everything in the present-day universe, the census falls dramatically short. So where did it all go? The leading suspect is a ghostly, vast web of incredibly hot and diffuse gas, a structure known as the warm-hot intergalactic medium, or WIM. Theorized to inhabit the spaces between galaxies, the WIM is not a cloud you could see or fly through. It is a superheated plasma, a thin soup of protons and electrons with temperatures ranging from hundreds of thousands to millions of degrees. This intense heat makes it incredibly difficult to detect, as it does not glow brightly in visible light. It is the cosmic equivalent of trying to spot a wisp of steam in a massive, dark room using only a faint flashlight. How do you find something that is both nearly invisible and spread across the unimaginable voids between galaxies? Astronomers have had to become detectives looking for the WIM's shadow. As the light from incredibly bright, distant objects like quasars travels for billions of years to reach us, it passes through these filaments of hot gas. The WIM does not block the light, but it does filter it. Atoms within this hot plasma can absorb very specific wavelengths of the quasar's light, leaving behind a unique, fine-line fingerprint in the quasar's spectrum. It is like analyzing a distant spotlight after it has passed through a particular kind of fog, looking for the specific colors that were filtered out to prove the fog was there. Another method is to search for the faint glow of the WIM in X-ray light, which this million-degree gas should emit. This is a painstaking task, requiring the most sensitive space telescopes to stare at the seemingly empty spaces between galaxies for long periods, hoping to catch a whisper of X-ray emission from the cosmic web itself. Finding this missing matter is not just about balancing the books. It is crucial for understanding the complete story of how galaxies formed and evolved. This warm, hot gas is the reservoir from which galaxies drew their material, and it is the environment into which they dump their processed matter through supernova explosions and galactic winds. The WIM is the circulatory system of the cosmos, and we are only just beginning to feel its pulse. Finding that missing ordinary matter requires reading the light from the most brilliant beacons in the cosmos, quasars. As this intense light journeys across billions of light years toward our telescopes, it passes through a labyrinth of invisible gas clouds and filaments. Each of these structures acts like a cosmic filter, absorbing a very specific fingerprint of light known as the Lyman alpha line. The result is not a single absorption line, but a veritable forest of them, a dense thicket of thousands of individual lines crowding the quasar's spectrum. This is the Lyman alpha forest, and it is one of the most powerful tools in cosmology. It provides a detailed core sample of the universe, a tomographic scan that slices across billions of years of cosmic history. Each line in this forest is a shadow, a ghostly silhouette of a single cloud or filament of hydrogen gas that the quasar's light has passed through. By meticulously decoding the pattern and spacing of these absorption lines, astronomers can reconstruct the three-dimensional distribution of this diffuse gas. They can map the vast, empty voids where the lines are sparse and trace the dense, tangled knots where the lines crowd together, revealing the locations of galaxy clusters and protogalactic clouds. This intricate absorption pattern is the ultimate evidence for the cosmic web, the grand architecture of the universe where galaxies are merely the bright jewels at the intersections of dark, massive filaments. The Lyman alpha forest lets us see the invisible scaffolding itself. It confirms that the missing baryons are indeed there, woven into this hot, diffuse web, tracing out the gravitational potential of the underlying dark matter. By studying this forest, we are not just finding lost matter, we are learning how the universe organizes itself on the largest possible scales, watching the flow of gas into and out of galaxies, and understanding the dynamic processes that have built the cosmic structures we see today. This spectral forest is a living record, a chronicle of the universe's growth written in the very light that travels through it. These brilliant cosmic lighthouses are quasars, the most powerful and persistent engines in the universe. A quasar is the intensely luminous core of a distant galaxy, where a supermassive black hole containing the mass of millions or even billions of suns is actively feeding. As vast quantities of gas, dust, and stars spiral into the black hole's accretion disk, the material is heated to millions of degrees by immense friction and magnetic forces, glowing with a ferocious brightness that can outshine the entire galaxy that hosts it. A single quasar can be thousands of times more luminous than our entire Milky Way, its light piercing across cosmic time to reach our telescopes. This makes them perfect beacons. By analyzing the light from these distant quasars, astronomers can study the composition and state of the universe when it was only a fraction of its current age, using them to illuminate the intervening cosmic web and map the distribution of the missing baryons in the Lyman Alpha forest. They are our probes into the deepest reaches of space and time, yet their existence presents a monumental puzzle. The most distant quasars we have observed existed when the universe was less than 1 billion years old. For a black hole to grow to billions of solar masses in such a short cosmic time is like a newborn baby weighing as much as a blue whale. Our standard models of black hole growth struggle to explain this. A black hole feeds at a limited rate governed by the Eddington limit, a point where the radiation pressure from its own feast pushes away the very material it is trying to consume. To reach such colossal sizes so quickly, the first black holes must have either started out incredibly massive from their very birth, as so-called direct collapse black holes, or they found a way to consume matter at super-efficient rates, bypassing the usual limits. How did the universe manufacture such monsters in its infancy? The answer may lie in the unique conditions of the early cosmos, where dense, pristine clouds of gas could have collapsed directly into massive black hole seeds without first forming stars. Or perhaps in that chaotic era, entire star clusters were swallowed whole in a single gulp. The enigma of quasars is not just about their incredible power, but about the frantic, violent childhood of our universe, a period we are only beginning to see through their brilliant, ancient light. Those brilliant quasars are like lighthouses shining through the final wisps of an ancient cosmic fog. This fog was the universe's default state for hundreds of millions of years after the Big Bang, a pervasive shroud of neutral hydrogen gas that scattered light and kept the cosmos in a featureless dark age. Then something dramatic happened, an event so transformative it changed the very nature of the universe. This was the epoch of reionization, the cosmic dawn when the first stars and galaxies ignited and began to burn the fog away. For the first 380,000 years, the universe was a hot, dense plasma, opaque and glowing. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms, creating a dark, neutral fog that stretched across all of space. This was the cosmic dark ages, the emergence of the first stars and galaxies, blazing with intense ultraviolet light, ended this long silence. Their radiation was so powerful it began to rip the electrons away from the hydrogen atoms, reionizing the gas and clearing vast, transparent bubbles in the cosmic fog. Imagine a landscape shrouded in a thick, global mist where suddenly brilliant lamps begin to switch on. Each lamp clears a small pocket of mist around it, and over time, these pockets grow and merge until the entire fog has lifted, revealing a universe of galaxies for the first time. This was not a gentle process. It was a violent and fundamental phase change for the cosmos, a battle between light and matter that shaped everything to come. The key mystery is identifying the precise sources of this transformative light. Were the primary culprits the first massive and incredibly luminous stars known as population 3 stars? These hypothetical giants, hundreds of times the mass of our Sun, would have lived fast, died young, and flooded their surroundings with ionizing radiation. Or were the first small galaxies, with their collective energy, the dominant force in burning through the hydrogen fog? Perhaps even those early quasars, powered by their supermassive black holes, contributed significantly to this great clearing. This is where our newest eyes on the cosmos come in. The James Webb Space Telescope is specifically designed to be a time machine peering back into this very era. Its powerful infrared instruments allow it to see the faint, red-shifted glow of those first stars and infant galaxies, objects whose light has been stretched into invisibility by the universe's expansion over billions of years. Every faint smudge of light Webb detects from this ancient epoch is a potential source of that reionizing energy, a candidate for one of the lamps that cleared the cosmic mist. By counting these early galaxies and measuring their brightness, astronomers are piecing together a timeline. How long did reionization take? Was it a swift, explosive event or a slow, drawn-out process that sputtered across the cosmos? The current evidence suggests it was largely complete by the time the universe was around 1 billion years old, but the details remain hotly debated. Solving the mystery of reionization is about more than just understanding a past event. It is about witnessing the moment the universe as we know it was truly born, the instant the lights came on and the stage was set for the grand cosmic drama of galaxy formation and evolution that would follow. We are now watching that dawn break in real time through the data streaming back from the edge of time itself. Those brilliant cosmic dawns revealed by the James Webb Space Telescope have unveiled a startling paradox. We expected to see the first faint infant galaxies, fragile and small, slowly gathering mass over billions of years. Instead, Webb found cosmic toddlers that look like full-grown adults. These galaxies, observed when the universe was less than 500 million years old, are breathtakingly massive, luminous, and mature. They contain vast numbers of stars, and some even show complex structures like disks and spiral arms, features that, according to our standard models, should have taken much longer to develop. It is like opening a family photo album and discovering pictures of your great-great-grandfather as a fully grown man, taken on the day he was born. This discovery sends a shockwave through our understanding of cosmic evolution. The prevailing model of galaxy formation is a slow, bottom-up process. First, dark matter forms invisible halos. Then, gas cools and falls into these halos, gradually pooling together to form the first stars. These small proto-galaxies then merge over vast cosmic timescales, building up into the large galaxies we see today. The galaxies Webb is seeing are far too big, far too soon. They simply did not have enough time, under the old rules, to accumulate so much mass and create so many stars. The early universe appears to have been working on fast forward. So what is happening? One possibility is that our understanding of the very first stars is wrong. Perhaps star formation in the early cosmos was incredibly efficient, converting nearly all available gas into stars in a single, furious burst. This would require conditions we do not see in the modern universe, where star formation is a slow, inefficient process, with most gas being blown away by stellar winds or supernova before it can collapse. Another, more radical idea involves the nature of dark matter itself. The standard model of cosmology uses what is called cold dark matter, particles that move slowly and clump together easily. But what if dark matter is not completely cold? What if it is slightly warm, meaning the particles move faster, making it harder for them to clump on very small scales? This warm dark matter could suppress the formation of many small dwarf galaxies, instead channeling material into fewer, but much larger, structures right from the start, creating giant galaxies almost instantly. There is even a chance our measurements of the universe's age are subtly off, or that we are misinterpreting the data due to exotic astrophysical processes we have not yet considered. The implications are profound. If these early giants are real and common, we may need to rewrite the first chapters of our cosmic history book. It forces us to question the fundamental processes that built the universe, suggesting that the infant cosmos was a far more dynamic and explosive place than we ever dreamed. The light from these ancient galaxies is not just showing us the past, it is challenging the very foundation of our cosmic story. This growing tension at the very foundation of cosmology is known as the Hubble tension, and it is a disagreement over one single, crucial number, the Hubble constant. This number represents the current expansion rate of our universe, the speed at which galaxies are receding from us for every megaparsec of distance. For decades, astronomers have strived to pin down this value with ever greater precision, but a strange thing has happened. The two most powerful and trusted methods for measuring it are now yielding stubbornly different answers, creating a crack in the bedrock of our cosmic model. One method looks back to the dawn of time, using the pristine snapshot of the cosmic microwave background from the Planck satellite. By carefully analyzing the subtle patterns in this baby picture of the universe, scientists can extrapolate forward through 13.8 billion years of cosmic evolution, using our well-tested model of cosmology to predict what the expansion rate should be today. This method provides a value of about 67 kilometers per second per megaparsec. The other method measures the universe directly in our modern cosmic neighborhood. It uses a cosmic distance ladder, building step by step from nearby stars to distant galaxies. Astronomers use pulsating stars called Cepheid variables, whose intrinsic brightness is linked to their pulse rate as standard candles. By measuring how bright these Cepheid stars appear in nearby galaxies, we can calculate their distance. Then, by observing how fast those same galaxies are moving away from us, we can calculate the expansion rate. This local measurement consistently gives a faster, higher value, around 73 kilometers per second per megaparsec. The difference seems small, but the precision of these measurements is now so exquisite that the chance of this being a simple statistical fluke is vanishingly small. The universe, according to its ancient light, should be expanding at one speed, but our local measurements tell us it is expanding significantly faster. It is as if you predicted a car's current speed based on a video of it leaving the factory, but when you look at your speedometer today, the reading is consistently higher. So what is causing this discrepancy? The most mundane possibility is that there is an unknown systematic error, a hidden mistake in one of the measurement techniques. Perhaps our calibration of the Cepheid stars is subtly off, or there is some unaccounted for dust in our galactic neighborhood affecting the supernova measurements. Teams of scientists have checked and rechecked these methods, hunting for any possible error, and the tension only grows stronger. This leads to the far more thrilling possibility that the Hubble tension is a real clue, a sign that our standard model of cosmology is incomplete. Perhaps dark energy is not constant as we have assumed, but is growing stronger over time, causing the expansion to accelerate faster than our models predicted. Or maybe dark matter possesses some strange, unknown property that changes how it behaves. There could even be a new type of neutrino or some other exotic particle from the early universe that subtly altered the cosmic recipe. This is not just a debate over a number, it is a potential window into entirely new physics, a signal that the universe still holds profound secrets about its own fundamental workings. The resolution of the Hubble tension will either expose a critical flaw in our observational methods or force us to rewrite the laws that govern the cosmos. This very same expansion rate, measured across the cosmos, finds a strange echo much closer to home in the behavior of our own robotic explorers. For decades, a ghost was haunting the outer solar system, an anomaly buried in the precise radio tracking data of the Pioneer 10 and 11 spacecraft. As these twin probes sailed beyond the orbits of Neptune and Pluto, traveling toward the endless void of interstellar space, NASA engineers noticed something deeply puzzling. Both spacecraft were experiencing a tiny but persistent and completely unexpected acceleration back towards the Sun. It was as if a faint, invisible hand had reached out and was gently tugging them backward on their journey into the abyss. This was the Pioneer anomaly. The force was incredibly small, less than a billionth of the gravity we feel on Earth, but it was undeniably there, and it defied all conventional explanation. For years, this minuscule drift captivated theoretical physicists, sparking a firestorm of exotic possibilities. Was it the signature of dark matter exerting a local gravitational pull within our solar system? Could it be evidence that our understanding of gravity itself, Einstein's theory of general relativity, needed a slight modification at the vast scales of the outer solar system? Some even proposed it was a consequence of the universe's expansion having a minute effect on objects within a gravitationally bound system like ours. The Pioneer anomaly became a beacon for those searching for cracks in the foundations of physics, a potential window into new laws of nature hiding in the deep cold of space. The mystery persisted for over 30 years, a tantalizing thread waiting to be pulled. The ultimate resolution, however, was not a revelation of new physics, but a masterclass in meticulous engineering detective work. A dedicated team of researchers spent years recovering old data from archaic formats and building a breathtakingly detailed computer model of the Pioneer spacecraft. They accounted for every conceivable force, from the subtle pressure of sunlight to the tiny thrust from the evaporation of lubricant on the spacecraft's spinning parts. The breakthrough came when they realized they had underestimated a much more mundane source of propulsion: thermal recoil. The plutonium in the probe's radioisotope thermoelectric generators was constantly decaying, producing heat that was used for power. This heat had to go somewhere, and it was radiated away from the spacecraft as infrared light. The team's sophisticated model showed that a slightly uneven distribution of this radiation, with just a little more heat bouncing off the back of the spacecraft's main antenna dish than from the front, would produce a net thrust. This tiny, photon-powered push was precisely in the direction of the Sun, and its magnitude was a perfect match for the anomalous acceleration. The ghost was not a new force of nature, it was the gentle, cumulative nudge of countless infrared photons. The story of the Pioneer anomaly serves as a profound cautionary tale for scientists probing the edge of known physics. It reminds us that before we invoke dark matter or rewrite the laws of gravity, we must first exhaust every possible mundane explanation, no matter how complex or subtle. The universe is full of genuine mysteries, but sometimes the most intriguing signals are echoes of our own creations, a whisper from the machinery we sent to explore the dark. Our own cosmic neighborhood presents a similar and deeply personal puzzle. Recent observations reveal that our Milky Way galaxy is not floating in an average part of the cosmos. Instead, we reside in a vast spherical region of relative emptiness known as the KBC void, named for the scientists who identified it. This local void is not a true vacuum, but it is significantly underdense, containing far fewer galaxies and clusters than we would expect. Its scale is staggering, stretching for over 2 billion light-years across, making it about 7 times larger than an average cosmic void. This discovery strikes right at the heart of the cosmological principle, the long-held assumption that the universe is smooth and uniform on the largest scales. If we are sitting inside one of the largest bubbles of nothingness in the observable universe, then our local perspective is fundamentally skewed. It is like living in a secluded valley and trying to measure the global population density. Your sample would be completely unrepresentative of the crowded cities and sprawling suburbs that lie beyond your isolated horizon. This cosmic address has profound implications for our greatest ongoing cosmic debate, the Hubble tension. The expansion of space is not perfectly uniform. Gravity from massive superclusters can tug and slow the expansion in dense regions, while the weaker gravity in voids allows space to expand more freely. Living inside the KBC void means we are in a region where the universe is expanding slightly faster than the global average. When we measure the Hubble constant locally, using supernova in our galactic backyard, we are measuring this faster local rate. Meanwhile, the measurement from the cosmic microwave background reflects the universe's average, slower expansion rate. Could it be that the entire Hubble tension is simply an illusion of our special location? Are we cosmic provincials mistaking the conditions of our local void for the nature of the entire cosmos? This forces us to confront a question we thought was settled centuries ago. The Copernican principle taught us that we do not occupy a special, central place in the universe. Yet here we are, living in a truly special and exceptionally large pocket of nothing. It is a humbling reminder that our view of reality is always filtered through our own unique and potentially misleading window. These ghostly giants drift through the cosmos, nearly invisible against the blackness of space. They are ultra-diffuse galaxies, and they defy everything we thought we knew about how galaxies are built. Imagine a cosmic phantom, a galaxy stretched to the same vast diameter as our own Milky Way, a sprawling disk of staggering proportions. Yet when you look for its stars, you find almost nothing. These spectral realms contain a mere 1% of the stars in a typical galaxy, leaving them so faint and transparent that you could practically see right through them to the universe beyond. Finding one is like spotting a single, dim light bulb floating in the middle of the ocean at night. Their discovery was a monumental surprise, forcing astronomers to question the fundamental recipes for galaxy formation. We always assumed that to build a large galactic structure, you needed a massive halo of dark matter to act as a gravitational anchor, pulling in vast amounts of gas which would then condense into a proportional number of stars. A big galaxy meant a huge family of stars. Ultra-diffuse galaxies break that rule completely. They have the size of a giant but the stellar population of a dwarf. So what happened? Why did these galaxies fail to light up the cosmos? One leading theory suggests they are cosmic failures, galaxies that started out with plenty of gas but had their star-forming fuel stolen away. In the violent environments of galaxy clusters, a young galaxy can be ripped clean of its gas as it plows through the hot, dense plasma that fills the space between galaxies. This process, called ram pressure stripping, acts like a cosmic wind, blowing out the very material needed to create new stars. The galaxy is left stranded, a vast, dark scaffold that never fulfilled its luminous potential. Another, even more intriguing possibility is that these galaxies are not failures at all, but are in fact dominated by dark matter to an extreme degree. They may be so utterly saturated with this invisible substance that their gravitational halos are incredibly massive and spread out, explaining their large size. Yet for reasons we do not understand, the normal matter within these halos simply refused to coalesce and form stars efficiently. Perhaps the gas was too hot or too turbulent, or maybe some early event prevented the calm, cool conditions needed for star birth. These ghostly galaxies are more than just cosmic curiosities. They are pristine laboratories for studying the mysterious influence of dark matter. Because they have so few stars, their dynamics are not complicated by the bright, messy interactions of stellar winds and supernova. This makes them ideal for measuring the gravitational pull of their dark matter halos directly, allowing us to map the invisible architecture of the cosmos with unprecedented clarity. The existence of ultra-diffuse galaxies presents us with a stark choice. Either our models of how dark matter gathers and guides the growth of galaxies are fundamentally incomplete, or we are witnessing the aftermath of a cosmic robbery on a galactic scale. Each of these faint, sprawling phantoms is a silent question, challenging us to explain how a galaxy can be so large and yet have so little to show for it. These ghostly galaxies drift through a cosmos we thought was predictable, but even their strange forms are overshadowed by something far more immense. Astronomers have begun mapping structures so colossal they defy the very rules of cosmic architecture. One of the most stunning is a formation known as the Giant Arc, a nearly symmetrical, crescent-shaped arrangement of galaxies, galaxy clusters, and clouds of intergalactic gas that stretches an almost unimaginable 3.3 billion light-years across the sky. To grasp that scale, if you could travel at the speed of light, it would take you more than 3 billion years to go from one end of this arc to the other. This structure is not a physical ring like Saturn's, but a connected filament of the cosmic web, a thread of gravitationally bound matter woven through the void. Its discovery was a shock because, according to our most fundamental rule of cosmology, the universe should not contain such things. The cosmological principle states that on the largest scales, the universe is homogeneous and isotropic. It should look roughly the same in every direction, with matter distributed in a relatively even, frothy pattern without any dominant, overarching structures. The Giant Arc is not a mere ripple in that foam, it is a tidal wave. Its sheer size is the problem. Cosmologists calculate a theoretical size limit for structures based on the age of the universe and the speed at which influences can travel. Essentially, there has not been enough time since the Big Bang for matter to have become organized through gravity into a single, coherent structure that spans such an enormous portion of the observable cosmos. The Giant Arc appears to be far larger than this calculated limit. Its existence suggests that either our understanding of the universe's initial conditions is flawed, or that some unknown, faster-than-gravity process helped sculpt the cosmos in its infancy. The immediate question is whether the Giant Arc is a true, physically connected structure or just a chance alignment, a cosmic mirage. Our eyes are excellent at finding patterns, even where none exist. We see faces in clouds and constellations in random star fields. Could this be the same phenomenon on a galactic scale? Perhaps we are simply connecting the dots between galaxies that are not truly bound, creating an illusion of a ring from unrelated points in the vast dark. Astronomers use powerful statistical tools to test this. They analyze the distribution of galaxies in that region of space, running simulations to see how likely it is for such a perfect, giant curve to form by random chance. The initial analyses suggest the probability is incredibly low, that the arc is a real feature of the cosmic web. Yet the debate is far from settled, and every new observation pushes the limits of what we consider possible. If structures like the Giant Arc are confirmed, they force a profound reevaluation. They hint that the universe might be textured with imprints from a time before the Big Bang, or that dark energy and dark matter interact in ways we have not yet imagined, creating gravitational potentials vast enough to sculpt the cosmos on scales we once thought were impossible. This is not just about finding a big ring in the sky. It is about discovering that the canvas of the universe itself might have a hidden grain, a structure written so large we are only just beginning to see it. This staggering mismatch between prediction and reality is the cosmological constant problem, a theoretical headache of almost unimaginable proportions. It begins with a simple, beautiful idea from Einstein that empty space itself can possess a fundamental energy, a cosmological constant that drives the universe apart. When we observe the acceleration caused by dark energy, we are essentially measuring the strength of this vacuum energy. The value we get from astronomy is incredibly small, a gentle, persistent push. Then we turn to our other great pillar of physics, quantum mechanics, to calculate what this energy should be. Quantum theory tells us that the vacuum of space is not empty at all. It is a seething, bubbling sea of activity where virtual particle pairs constantly pop into and out of existence. Every cubic centimeter of seemingly empty space should be boiling with this quantum foam, and all this frantic activity should be contributing to the energy density of the vacuum. When physicists perform the calculation, adding up all the potential contributions from every known quantum field. The result is a number that is 1 followed by 120 zeros larger than the value we actually observe. This is not just a small error, it is the most spectacular failure of a prediction in the entire history of science. To put this incomprehensible number into perspective, the difference between the theoretical prediction and the observed reality is greater than the difference in scale between a single proton and the entire observable universe. It is as if our best theories predicted that a single breath should contain enough energy to blow up 1,000,000 galaxies, yet in reality, it barely rustles a leaf. This is not a minor puzzle, it is a screaming contradiction at the heart of modern physics, suggesting that something is profoundly wrong or missing from our understanding. How can two of our most successful and well-tested theories, general relativity and quantum mechanics, be so catastrophically incompatible on this one fundamental point? The hunt for a solution has led to some of the most daring and as yet unproven ideas in theoretical physics. One prominent line of thinking involves a delicate cancellation mechanism. Perhaps there are many different fields contributing to the vacuum energy, some with positive values and some with negative, and through some unknown principle, they almost perfectly cancel each other out, leaving behind only the tiny, leftover residue we detect as dark energy. The problem is that this cancellation would have to be fine-tuned to 1 part in 10 to the 120th power, a level of precision that seems absurdly unnatural. Another radical proposal is the anthropic principle within the multiverse. If there are an infinite number of universes in a multiverse, each with a randomly determined cosmological constant, then only in the rare universes where this value is incredibly small, like ours, would galaxies and life ever have a chance to form. In this view, the constant is not fine-tuned for us. We simply exist in one of the few habitable bubbles where the numbers are just right. For many scientists, this is an unsatisfying answer, as it replaces a physical explanation with a statistical one. Other theories suggest that gravity behaves differently on the largest scales, or that our conception of the quantum vacuum is fundamentally flawed. Some even propose that dark energy is not a property of the vacuum at all, but a new, dynamic field that we have yet to identify. Each of these ideas is a testament to human ingenuity, but none has yet produced a testable prediction that would resolve the crisis. The cosmological constant problem remains a silent, gaping hole in our model of the universe, a constant reminder that for all our knowledge, we are still gazing into a profound and beautiful darkness. That screaming contradiction in the vacuum of space finds a terrifying echo at the edge of a black hole. Here, the two great pillars of modern physics, general relativity and quantum mechanics, enter into a direct and violent conflict. It is a battle over the most fundamental currency of reality, information. According to Einstein's theory, a black hole is defined solely by its mass, spin, and charge. If you were to throw a grand piano, a library of encyclopedias, or a box of confetti into a black hole, the result would be identical. The black hole would simply grow slightly more massive, and all the intricate information about what fell in, the structure of the piano, the words in the books, would be utterly and permanently erased from our universe. This is a catastrophe for quantum mechanics, which holds a sacred rule: information cannot be created or destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. The black hole information paradox asks a simple, devastating question: where does the information go when it crosses the event horizon? For decades, this was considered an unanswerable puzzle. Then Stephen Hawking made a discovery that deepened the mystery before offering a potential way out. He realized that black holes are not completely black. Due to weird quantum effects at the very edge of the event horizon, black holes slowly leak radiation, a faint hiss of particles now known as Hawking radiation. This radiation causes the black hole to gradually lose mass and over eons evaporate completely. The problem is, Hawking initially showed that this radiation is purely thermal. It is random noise, carrying no information whatsoever about what fell in. So when the black hole finally vanishes, all the information it ever consumed vanishes with it, permanently violating quantum law. This is the paradox in its sharpest form. How can the universe preserve information if a black hole can destroy it? One of the most mind-bending solutions is the holographic principle. It proposes that all the information describing the three-dimensional volume inside a black hole is actually encoded on its two-dimensional surface, the event horizon. Imagine the information about every object that falls in is not lost, but is smeared like a pixelated tattoo across the boundary of the hole, preserved forever in a holographic film. Then, as Hawking radiation escapes, it is not random, but is subtly imprinted with this surface information, slowly and chaotically decoding the history of the black hole's diet back into the universe. The information was never truly inside the black hole. It was always on the surface, and it escapes, scrambled beyond recognition, in the radiation. This leads to a truly wild speculation. If a black hole is a one-way street where matter and information vanish, could its theoretical opposite exist? This is the idea of a white hole, a region of space-time where nothing can enter, but from which matter and energy can only erupt. A white hole would be like a black hole running in reverse, spewing out everything it had ever consumed in a violent cosmic rebirth. In theory, a white hole could be the other end of a black hole's wormhole, or it could be how a new universe is born from the collapse of a black hole in a parent cosmos. Perhaps the information that falls into a black hole in our universe does not vanish, but is instead fired out into a new reality through a white hole. While mathematically possible within general relativity, white holes are considered highly unstable and likely cannot exist in our universe for more than a fleeting instant. No white hole has ever been observed, yet they remain a tantalizing thought experiment, a cosmic escape hatch for information, and a dramatic reminder that at the very edge of physics, even the most absolute of boundaries might have a hidden back door. This holographic principle, born from the fiery paradox of black holes, proposes a reality so strange it defies all intuition. It suggests that our rich, three-dimensional world, with its swirling galaxies, towering mountains, and the very thoughts in your mind, might be nothing more than a magnificent illusion. All the information needed to describe every event within a volume of space could be perfectly encoded on its two-dimensional boundary, like a cosmic DVD. The universe we experience would then be a holographic projection, a breathtakingly detailed and immersive movie playing out from data stored on a distant, flat screen. This idea first emerged from the black hole information paradox. Physicists realized that the maximum amount of information a black hole can contain is not proportional to its volume, but to the area of its event horizon. This was a radical break from common sense, where information capacity should grow with the volume of a container, like filling a larger hard drive. For a black hole, the ultimate container, the real hard drive is its surface. This led to a staggering extrapolation. If the most information-dense objects in existence obey this area law, then perhaps every region of space does too. Our entire universe, with its vast three-dimensional expanse, might be a projection from a two-dimensional surface at the cosmic horizon. Think of a credit card hologram, a flat sticker that creates a shimmering, three-dimensional image. The holographic universe theory proposes that reality itself works in a similar way. The world we touch and see is a phenomenal projection, while the true, fundamental reality is a vast, complex network of information painted on the spherical shell of our observable universe. This is not just a philosophical idea, it has a concrete mathematical foundation in string theory. In one of the most successful realizations of the holographic principle, physicists have created a precise duality. They found that a theory of gravity operating in a hypothetical 5-dimensional space is completely equivalent to a quantum field theory without gravity operating on its 4-dimensional boundary. It is a perfect dictionary, translating problems that are impossibly difficult in one realm into solvable equations in the other. This means that the messy, complex interactions of particles and forces in our 4-dimensional world could be a different way of describing the elegant dance of strings and gravity in a higher dimensional reality. The implications are dizzying. If the holographic principle is true, then the fundamental building blocks of reality are not particles or strings existing in space, but bits of information like the ones and zeros in a computer. Space-time and gravity would not be fundamental, but would emerge from the complex entanglement of this cosmic information network, much like the smooth display of a video game emerges from the underlying code. So how could we ever test such an outlandish idea? Scientists are looking for subtle signatures in the most precise observations we have. One place to search is the cosmic microwave background. The holographic principle predicts a specific, faint pattern in this ancient light, a particular kind of noise that differs from the predictions of standard inflation. Another avenue involves studying the fabric of spacetime itself with gravitational wave detectors. If spacetime is granular at the tiniest possible scale, the Planck scale, then very high-energy gravitational waves might travel at slightly different speeds, a subtle effect that future observatories might one day detect. The most profound implication of all is that the universe is not a container for things and events. It is a relationship, a cosmic computation where the perception of depth, time, and substance is a magnificent and deeply convincing rendering. Deep within the silent voids between galaxies, a sudden scream of energy erupts. For a few fleeting milliseconds, a single point in the sky releases more power than our sun puts out in 80 years. Then, just as suddenly, it vanishes back into the cosmic background. These are fast radio bursts, and they are one of the most explosive and perplexing mysteries in modern astronomy. The first FRB was discovered only in 2007, a lone spike in archival data that seemed almost too strange to be real. Since then, we have detected hundreds of these events, some from sources that erupt repeatedly in unpredictable patterns, while others are one-off cataclysms. The key to their mystery lies in their dispersion. As these radio waves race across billions of light years, they pass through the sparse electrons of the intergalactic medium. This causes the different wavelengths of the burst to slow down by slightly different amounts, spreading the signal out. By measuring this spread, astronomers can calculate the total amount of material the burst has traveled through, giving them a direct measure of its staggering distance. We now know these bursts originate from other galaxies, some so far away their light has been traveling for most of the universe's history. So what natural cosmic engine can possibly produce such an intense, brief flash from such incredible distances? The leading suspect is a magnetar, a type of neutron star with an unimaginably powerful magnetic field. A magnetar's magnetic field is a quadrillion times stronger than Earth's, and it is thought that starquakes on its solid, ultra-dense crust could release titanic fractures, unleashing the energy of an FRB in a single magnetic convulsion. We have even detected an FRB from within our own galaxy that was linked to a known magnetar, providing the first solid clue, but are magnetars the only source? Some FRBs are so enormously energetic that they push the limits of what even a magnetar is thought to be capable of producing. This has opened the door to more exotic and violent possibilities. Could they be the product of two neutron stars merging, their final, deadly embrace sending a shockwave through the surrounding cosmos? Or perhaps they are the birth cries of new black holes, or the result of cosmic strings, hypothetical defects in the fabric of spacetime, snapping like overstretched rubber bands. Some have even dared to speculate about artificial origins, though most scientists consider natural explanations far more likely. Yet beyond the question of their birth, FRBs have become an unexpected gift to cosmologists. Because their signals carry the fingerprint of every electron cloud they pass through, they act as perfect probes for the invisible material between galaxies. Each burst is like a single, brilliant flash of lightning in a dark forest, illuminating the structure of the trees for just an instant. By studying how the signal from a single FRB has been dispersed and scattered, astronomers can map the distribution of the missing baryonic matter in the cosmic web, weighing the tenuous filaments of the warm, hot intergalactic medium that have been so difficult to detect by any other means. These mysterious flashes are not just cosmic puzzles, they are becoming the flashlights we use to explore the darkest, most empty spaces in the universe. This strange alignment is not limited to the grandest scales of the cosmos. It appears in our own celestial backyard, in the very motion of the galaxies that orbit our own. The Milky Way is not a solitary island. It is the heart of a small empire surrounded by dozens of smaller satellite galaxies like the Large and Small Magellanic Clouds. For a long time, we assumed these satellites were swarming around us in a random, chaotic cloud, much like bees around a hive. Then we started mapping their paths with greater precision. The result was a profound shock. Many of these satellite galaxies are not moving randomly at all. Instead, they are aligned within a remarkably thin, coherent plane, a vast disk-like structure that rotates around the Milky Way. It is as if our galaxy is not just a spinning pinwheel of stars, but the center of a gigantic, invisible carousel, with its companion galaxies all riding on the same immense merry-go-round. This discovery, often called the disk of satellites problem, strikes directly at the core of our most sophisticated cosmological simulations. These computer models, which use our best understanding of dark matter and gravity to simulate the evolution of the universe, consistently produce a very different result. They predict that the satellites of a galaxy like the Milky Way should arrive from all directions, following independent, chaotic orbits that form a roughly spherical cloud. The fact that we observe a thin, rotating plane is a glaring anomaly. It suggests that something fundamental is missing from our virtual universes. So what could be causing this strange, coordinated dance? One possibility is that our models of dark matter are incomplete. The standard cold dark matter model works beautifully on the scale of the entire cosmos, but perhaps it fails on the smaller scales of galactic neighborhoods. If dark matter particles interacted with each other through some unknown force, not just gravity, it could cause them to settle into disks, which would then shepherd the visible satellite galaxies into a similar plane. Another, more radical idea involves the cosmic gas flows from which galaxies form. Perhaps the Milky Way and its satellites all condensed from a single, vast, rotating cloud of primordial gas, preserving that original spin in their orbits to this day. This would be a fossil from the birth of our galactic system, a memory written in the paths of its companions. Yet another theory suggests these satellites are not ancient, independent galaxies at all, but were all torn from a larger galaxy that ventured too close to the Milky Way in the distant past, their shared origin explaining their common orbital plane. Each of these explanations faces its own challenges, and none has yet achieved a clear consensus. The silent, coordinated rotation of these dwarf galaxies is a quiet but persistent challenge to our cosmic models, a ghostly carousel whose motion we can see, but whose music we cannot yet hear. Out in the deepest voids, the universe is constantly bombarded by invisible bullets. These are cosmic rays, atomic nuclei hurtling through space at nearly the speed of light. The most energetic of these particles carry as much force as a professionally pitched baseball, all compressed into a single, subatomic speck. For decades, physicists predicted a hard limit for how much energy a cosmic ray could retain over intergalactic distances, a barrier known as the GZK cutoff. It is a cosmic speed limit imposed not by law, but by the faint, cold glow of the universe's oldest light. The logic is simple. a proton traveling across billions of light years will inevitably collide with the photons of the cosmic microwave background, the relic radiation from the Big Bang. Each of these collisions is like a high-speed bullet striking a cosmic rain droplet, sapping a little of the bullet's energy. For a cosmic ray from a distant galaxy, these countless, tiny interactions should drain its energy long before it reaches us, ensuring we never detect particles above a certain threshold. This is the GZK cutoff, a fundamental ceiling written into the laws of physics. Yet our detectors on Earth have recorded a handful of these cosmic bullets with energies far beyond this predicted limit. They have somehow cheated the cosmic speed limit, arriving with an impossible punch. This is the mystery of the ultra-high-energy cosmic rays. How did they cross such vast distances without slowing down? One possibility is that they did not have far to travel. Perhaps their sources are relatively close within our own local supercluster of galaxies, where the journey is short enough to avoid significant energy loss. But that only deepens the puzzle, because what kind of cosmic engine sitting in our galactic neighborhood could possibly accelerate a single particle to such an insane velocity? The prime suspects are the most violent objects we know, active galactic nuclei, where supermassive black holes devour entire stars and generate jets of plasma stretching for millions of light years, could act as natural particle accelerators of unimaginable power. Or perhaps the culprit is a supermassive black hole merger, an event so cataclysmic it could warp space-time itself into a slingshot. There are more exotic candidates too. Some theorists suggest these particles are not accelerated at all, but are instead the decay products of super-heavy dark matter. In this scenario, a single primordial dark matter particle, left over from the Big Bang and weighing as much as a bacterium, could spontaneously decay, releasing its immense mass energy in the form of an ultra-high-energy proton. Each of these impossible cosmic rays is therefore a messenger, a calling card from the most extreme processes in the universe, or perhaps even a clue to the nature of dark matter itself. Their existence forces us to ask whether our understanding of particle physics holds up at these ultimate energies, or if we are witnessing the signature of something entirely new. These cosmic messengers carry with them the elemental history of everything. To trace their origin, we must journey back to the universe's first few minutes, to a time of almost unimaginable heat and density. This was the epoch of nucleosynthesis, the moment the first atomic nuclei were forged. The entire cosmos was a searing, primordial soup of fundamental particles, a plasma so hot that not even protons and neutrons could stick together. As the universe expanded and cooled in those first critical minutes, a brief window opened. For about 17 minutes, the temperature was just right for nuclear fusion to occur, but the universe was still too hot and dense for these new nuclei to capture electrons and become stable atoms. During this fleeting cosmic moment, protons and neutrons collided and fused, creating the first seeds of matter. The result was a universe composed of about 75% hydrogen and 25% helium by mass, with only the barest trace of lithium. This predicted mix is one of the strongest pillars of evidence for the Big Bang theory. It is a precise chemical fingerprint left over from creation, and when we look at the oldest stars and the most distant, pristine gas clouds, we find that fingerprint matches almost perfectly. The universe's elemental recipe is exactly what we would expect from a hot, dense beginning. Yet there is one stubborn ingredient that does not fit. The amount of lithium we observe is only about 1/3 of what our models predict. This is the lithium problem. The calculations for Big Bang nucleosynthesis are exquisitely precise, grounded in our well-tested knowledge of nuclear physics. They tell us exactly how much lithium-7 should have been created in that first nuclear furnace. But when we measure the abundance of lithium in the atmospheres of the most ancient stars in our galaxy, stars that formed from nearly pure primordial material, the number is consistently and bafflingly low. It is as if a master chef followed a perfect recipe, but one key spice was always missing from the final dish. So where did the lithium go? One possibility is that our understanding of the nuclear reactions themselves is incomplete. Perhaps there is an unknown nuclear pathway that destroyed lithium as quickly as it formed in those first few minutes. Another line of thought points to the stars themselves. Could these ancient stellar bodies somehow process and destroy lithium over their immensely long lifetimes, altering the primordial signature we see today? The most thrilling possibility is that the lithium problem is a direct hint of new physics. The predictions depend critically on the number of different types of neutrinos and their properties. What if a previously unknown type of neutrino, a sterile neutrino, was present in the early universe, subtly altering the nuclear reactions? Or perhaps it points to something even more exotic, like the influence of certain dark matter particles that interacted with normal matter during nucleosynthesis, throwing off the delicate balance. This tiny discrepancy in the amount of a single light element is a persistent whisper from the dawn of time, suggesting that our picture of the universe's first moments, for all its success, might still be missing a crucial piece of the puzzle. This particle horizon is our ultimate prison wall, built not from matter but from time and light. We are forever trapped within a bubble of causality, a sphere of observation exactly 13.8 billion light-years in radius. The universe we can see, with its hundreds of billions of galaxies, is simply the region from which light has had time to reach us since the dawn of time. But the most profound and humbling truth is that this cosmic bubble is almost certainly not the entire universe. There is a beyond. We can use the laws of physics to theorize, to run the equations, but we can never, ever receive a single photon, a single shred of data from what lies outside. It is the final, impenetrable veil. So what could it be like out there? One possibility is a simple and staggering extension of our own reality. The universe beyond the horizon could be an infinite, more or less uniform continuation of the cosmic web we see here. More filaments of dark matter, more glittering galaxies, more vast, empty voids, stretching on forever in a cosmic pattern without end. In this view, our observable universe is just one random patch in an infinite tapestry, no more special than a single grain of sand on an endless beach. But there is another, far more unsettling possibility. The laws of physics that govern our bubble, the strength of gravity, the mass of an electron, the very number of dimensions, might not be universal constants at all. They could be local bylaws set by the random conditions of our particular patch of spacetime during the inflationary Big Bang. Beyond our horizon, the fundamental rules could be different. In another bubble, gravity might be 10 times stronger, preventing stars from ever forming. In another, the nuclear forces might be too weak to bind protons and neutrons, leaving a universe of featureless plasma. Some of these alien universes might be stillborn, collapsing instantly into a big crunch. Others might be so wildly different that matter as we know it is impossible. This idea transforms the cosmos from a single, coherent entity into a potential multiverse of cosmic domains, each with its own unique physics, its own potential for life, or its absolute prohibition of it. We are left with a haunting, unanswerable question. Is our universe a lonely island in an endless sea of nothing? Or is it just one room in an infinite, chaotic mansion where every door opens to a different reality? The silence from beyond the horizon is absolute, and it is the loudest mystery of all. This final frontier is not a place in space, but a question at the very limit of thought. After journeying through the cosmos's grandest enigmas, from dark energy to the multiverse, we arrive at the ultimate mystery. Why does anything exist at all? Why is there a universe with its galaxies, its laws, and us, rather than a silent, eternal, and absolute nothing? This is not merely a philosophical curiosity, it is a scientific problem that probes the initial conditions of the Big Bang itself. Our entire cosmic story begins with a singular event, but physics cannot tell us what happened before that, or why the universe was born with such exquisitely fine-tuned properties. The fundamental constants of nature, the strength of gravity, the mass of an electron, the force that binds atomic nuclei, appear to be perfectly calibrated for complexity. If gravity were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch long before stars could form. If the nuclear force were marginally weaker, hydrogen would be the only element, and the periodic table and the chemistry of life would be impossible. This cosmic fine-tuning is so precise it seems to demand an explanation. One possibility emerging from the frontiers of quantum gravity is the concept of a universe from nothing. In this view, the nothing of physicists is not an empty void, but the absence of space, time, and matter altogether. Quantum mechanics allows for particles to spontaneously pop into existence from an energy vacuum, a phenomenon we observe constantly. Could the entire universe be the ultimate example of this, a colossal quantum fluctuation that simply happened? Perhaps the net energy of the cosmos is precisely zero, with the positive energy of all matter and radiation perfectly cancelled out by the negative energy of gravity, making the entire universe a free lunch. This idea suggests that a universe like ours could and would naturally arise from such a quantum event. Yet this only pushes the mystery one step further. Why are there quantum laws that permit such a thing? Why is there a framework of physics that allows for spontaneous creation? We are left staring into an abyss of infinite regression, where every answer simply begs a deeper, more fundamental question. This may be the final wall we cannot scale, the ultimate horizon of human understanding. The cosmos presents us with 30 profound mysteries, but this one stands apart. It asks not how the universe works, but why it is. And in the face of that question, science and philosophy meet at a silent edge, humbled by the simple, staggering fact that there is something rather than nothing for us to ponder at all. From the humbling limits of our observable bubble to the staggering possibility of an infinite multiverse, this journey across 30 cosmic mysteries reveals a universe far stranger and more wondrous than we ever imagined. We have stood at the edge of physics, where dark energy pushes the cosmos toward a cold, lonely end and dark matter sculpts galaxies in the shadows. We have questioned the very nature of reality, exploring whether our universe is a holographic projection or one bubble in a frothing cosmic ocean. Each unanswered question, from the great cosmic flows that pull our galaxy to the ghostly whispers of the cosmic microwave background, is not a dead end. It is a new frontier, a doorway to a deeper understanding that awaits the next generation of explorers, the next revolutionary telescope, the next spark of human curiosity. The universe is not a completed puzzle, but a living, expanding story, and we are all part of its ongoing discovery. So, which of these 30 mysteries captured your imagination the most? Was it the terrifying potential of a big rip, the ghostly dance of ultra-diffuse galaxies, or the profound silence from beyond our particle horizon? Let us know your favorite in the comments below. If you enjoyed this tour to the very edge of everything, please give the video a like to help others find it, and subscribe for more deep dives into the wonders of our cosmos.